Good afternoon, class. We are looking at module 4, covering chapters 8 and 9. Chapter 8, hypothesis testing. All right, let's start with the basics. A test of hypothesis is always about a population parameter. It's important to know in statistics, basically everything is about the population. However, on a normal basis, we don't have access to it. So everything is about population parameter. The observed value of a test statistic is the value that we calculate for a sample statistic. So it's calculated. As the sample size gets larger, both type 1 and type 2 errors decrease or increase. They always decrease because the best way to reduce error is to pick a larger and larger sample size. Define type 1 error. Rejecting a null hypothesis when it's true, also known as false positive. Define type 2 error. Failing to reject a null hypothesis when it is false, false negative. The value of alpha is called probability of type 1 error, or the significance level of the test, which is equal to the probability of type 1 error. The value of beta is equal to the probability of type 2 error. 1 minus beta is called the power of the test, which is the correct decision, probability of rejecting a false hypothesis. Could somebody read this question, please?
In 1990, 5.8% of job applicants who were tested for drugs failed the test at the 0.01 significance level test. The claim that the failure rate is lower if a simple random sample of 1,520 current job applicants result in 58 failures. Does the result suggest that fewer job applicants now use drugs?
Perfect. To do that, there are a number of steps we have to take. And so what I want to do, I want to first translate this because this is word problem. And then I want to tell you how the test of hypothesis is done in general. So this is a binomial distribution because there are two outcomes. They test positive or negative. So when it's a binomial distribution, we need to know N and P. This is 5.8%, so P is 0.058, 5.8%. Significance level. Alpha is 0.01. 1,520 randomly, a sample of 1,520. N is 1,520, and 58 of them fail. That X is 58. So this is a binomial distribution. P is 0.058, which makes Q 1 minus that, 0.942, 1 minus that. And it is important to multiply that by N, and it has to be larger than or equal to 10, so we can use ND or normal distribution. Again, binomial distribution can be approximated by normal distribution as long as the product of NP and NQ are large. In some instances, they take it to be 5. In more, they take it to be 10. Also, we can calculate the P hat, which is X over N, 58 over 1520, and we are ready to move on. And also, the test statistic has this formula. You can pick it up from the formula sheet. Z equals P hat minus P over the square root of PQ over. Now, notice A, B, C, D. Those are the 4 steps that basically I'm going to use with the test of hypothesis. So even if they don't ask you to do those in that order, it must be done, and I will show you. And then I'll add the p-value and the concept of a type 1 error. So step 1, you write H0 and H1. In some text, they use HA, the alternative. H sub 0 is the null hypothesis. H1 or HA is the alternative hypothesis. And then you write which one is the claim, and you write the number of tails. If it's left tail test, right tail test, two tail test. I'll explain it to you in a moment. The next step is to calculate TS, test statistic. This has a formula. For example, in the case of a proportion, here's the formula picking up from the formula sheet. Then you use CV, critical value. How do you arrive at it? Using alpha. The choice of alpha will give you the critical value either from the table or technology. For example, in this case, since we are going to go with Z being P hat minus P over the square root of PQ over N for the second step, for the third step, we are going to use the Z table. Finally, we make a decision. Decision has 3 parts to it. Number 1, you are going to reject or not reject H0, fail to reject, which means everything that we do, steps 1, 2, 3, is about H0. You make a decision about H0. Then you can expand it to say whether the claim is true or false, and then you restate it. And by the way, if you reject H0, that means H0 becomes a false, H1 or HA becomes true, and vice versa. So we look at this question. We want to come up with the first 4 steps. So here's how we are going to write it. H0, P is 0.058. And what is H1? Test the claim that the failure rate is now lower. That means H1P is lower, less than 0.058. So that's the first step. And notice the notation. First and foremost, you never ever use sample statistics such as P hat. You always use population parameters such as P, mu, sigma. So for this one, if you wrote greater than or equal, it's okay because it's complementary to less than, but I highly recommend you keep it as equal depending on the text. This is less than because it says so. And this is the claim, again, as we read the question, this is the claim. Why is this LTT, left-tailed test? Because less means left. I'm going to show you with a graph. So that's the first step, A. We need to do that. The second step is to calculate the test statistic using this formula. That's where the given comes from. So P hat, we have it here, minus P over the square root of a PQ over N. $15.20. All right. We get negative 3.309. So that's the second step. So first step is H0, H1. Second step is TS, short for test statistic. The third step is the critical value CV. Alpha is 0.01. It's a left tail test. So everything is on the left side. So this tail ends up being negative 2.33 or negative 2.325. This is the number. Since there are two and it may be confusing, let me just do this quickly. So you draw this, and this is rough sketch. This tail is equal to alpha or 0.01, and using technology or table, this z value is a negative 2.325. The next part is making a decision. So this is the traditional method by which we compare two numbers. What numbers? The critical value and the test statistic. So where does this go? Again, this doesn't have to be to scale. This value was negative 2.325. This goes to the left of it somewhere here. That's why I had this graph for you. So this is the critical value. This is the test statistic. So let me this is CV. This is test statistic. I'm going to make a decision. There are three parts to it. Because test statistic is way into the rejection region, we are going to reject H0. One more time. Test statistic in a matter of comparison to the critical value, because it's in the tail, reject H0. If it was in this vicinity, fail to reject H0. So if you're rejecting H0, loosely put, you're accepting H1. If you're accepting H1, then you're accepting the claim. The claim becomes true. And then you rewrite. The way you rewrite is very simple. There is or there is not. In this case, there is sufficient evidence to support the claim. And you do the writing. So take a look. Reject H0 because the value of test statistic is inside the rejection region. If you're rejecting H0, you have to go to the first step to see where the claim is. Since the claim doesn't belong to H0, it belongs to H1, becomes true. Then there is sufficient evidence to support the claim that the failure rate among job applicants for drugs is now lower. Results suggest that fewer job applicants now use drugs. This is it. However, I want to discuss this from a different point of view, because in this step, we may use the p-value. And for that reason, we may not even look up the critical value. And the way it works, this number has been calculated. And because it's a left-tail test, the area to the left of that becomes your p-value, and you compare it to alpha. So let's go over that method. So you do it by the method they ask you. Most of the time, technology does that. So I want to find the p-value and make a decision. Is this decision in agreement with the previous one? Well, first, let me explain about the p-value. When we go through the process, it's either left-tail test or right-tail test or a two-tail test. If it's a left-tail test, the p-value is area to the left of the test statistic. If it's a right-tail test, to the right of test statistic. And if it's two-tail test, it's either to the left or right of the value that you calculate, and you must multiply by 2. So the p-value is twice the area to the left of the test statistic, or twice the area of the right to the right of the test statistic if it's a two-tail test. This is a one-tail test, and therefore the p-value is the area to the left of the test statistic, which was negative 3.309. So, or roughly negative 3.31, so this area. So looking up the table or using technology, we get 0.0005. Now, in the case of a critical value, we compare two numbers, the critical value to test statistic. In the case of a p-value, we compare two areas. This represents an area. If it's less than alpha, you reject the null hypothesis because it puts you in the rejection region. And I hope you recall that alpha was here. If you remember in the previous page, the CV was like negative 2.33. And so this area, which is alpha, is larger than the red area, which is the p-value. And so decision criteria for p-value method. P-value, we found it to be 0.0005. Since it's less than alpha, which was 0.01, if you recall it was 0.01, then we reject the null hypothesis, which is the same decision we made. What is the type 1 error? What is the probability of making type 1 error? The probability of making type 1 error is always equal to the choice of alpha, which happened to be 0.01. But what is type 1 error? Let's remind everybody, rejecting H0 when H0 is true. So type 1 error for this case would be rejecting the claim that the failure rate of job applicants who were tested for drugs is 5.8% when the percentage is actually 5.8%. And as I mentioned, the probability of type 1 error is always equal to alpha, and since the choice of alpha was 0.01, the answer is 0.01. Now, it's important to understand the process and write the steps. However, certain parts can be done by technology. For example, with the TI calculator, we can do one proportion z-test, and we plug it in. So they're asking for p, we put 0.058. That means really H0 in essence. What is the value of p? X was 58, N was 1520. And it was less than, because you have a choice. You can go with not equal, which makes a two-tailed test, less than, which is left-tailed test, or greater than, which is right-tailed test. When you calculate, it gives you this, and what I want you to pay attention to is the following. If you look at this value, this is the test statistic, which we calculated. And as you can see, it's very close. Of course, why is it somewhat different? Because this comes from the table. This is using many, many, many more decimals. This P is the p-value, and I hope you realize this means 4.6727354 times 10 to the power of minus 4. So this means, I want to make sure that everybody understands, the meaning of this P is, let's say 4.67 times 10 to the power of minus 4, and this is scientific notation. You have to move it this way 4 places, and it becomes 0.00000467. As you can see, this is very close to this if you do the rounding. So that is using technology. We're going to look at more examples, and you'll see that we're going to repeat the same process. Could somebody read this, please? All right. A sample of 54 bears has a mean weight of 182.9 pounds. Let's assume that the standard deviation of weights of all such bears is known to be 121.8 pounds at alpha of 0.1. Is there enough evidence to support the claim that the population mean of all such bear weights is less than 200 pounds? So again, there are 4 steps. We're going to go through all those 4. Number 1, we are going to write the given. A sample of 54, n is 54, has a mean of 182.9 pounds. So this is the mean. This is X bar. Why is it? Because it goes back to those 54. So this is X bar, not mu. Let's assume the standard deviation for all, that means sigma for all, for the population, is 121.8. Alpha is 0.1. And we're going to test the claim that the population mean of all such bear weights is less than 200 pounds. So mu is 200 pounds. So here's the given. So the very first step, H0 and H1. Let's see how we're going to write that. Because it's the average, the mean, so mu is 200. H1 mu is less than 200 because it says so, less than. This is what we are checking. And it happened to be the claim, and it's left tail test again. It may not be the case always that it's left tail test, or the claim goes with H1. Sometimes it may go with H0. So you want to be very careful as you read this. The second step is test statistic. The test statistic, you have a formula sheet, z equals x bar minus mu over sigma over square root of n. So this is the formula for test statistic. So let's plug in, replace the x bar with 182.9 minus mu, which is 200, over sigma 121.8 divided by square root of n54, and you plug it into a calculator, and it gives you the following number, negative 1.0317. So I hope you see we are repeating the same process. Step 1, H0, H1. Step 2, test statistic. Step 3, we're going to go with the CV. CV comes from the choice of alpha, which is 0.1. And it gives us the Z of negative 1.285. This comes from the Z table. So let me first do this by hand. I'll show you a better graph in a moment. So far, it's a left tail test. This is alpha of 0.1. And this is the critical value of Z being negative 1.285. Now, here's the test statistic. If it's in this, if you throw it in here, it's in rejection region. If you throw it in here, it's not. And I hope you see that this goes somewhere here. It doesn't have to be to scale, so somewhere here. It's a non-rejection region. So let's do this graph and let's clean this up. So this is your critical value. Alpha is 0.1, CV is negative 1.285, and this is not to scale. And this is your test statistic of negative 1.0317. And that, compared to this point, it's in the non-rejection region. So this is alpha, negative 1.285 is this, and test statistic is somewhere here. Okay. Therefore, fail to reject the null hypothesis. Why? Because the test statistic in it is in a non-rejection region. So if you don't reject the null hypothesis, you're rejecting the alternative. Therefore, anything that goes with that is rejected. The claim is rejected, it makes the claim false. And then you write down, there is not sufficient evidence to support the claim, and you just pick it up from here and do the writing. So take a look, see how we do that. Fail to reject the null hypothesis because the value of test statistic is inside the non-rejection region, somewhere here. Therefore, you go back to the first step and you look at it. If you're not rejecting H0, you're rejecting H1, you're rejecting the claim becomes false. And now that the claim is false, there's not sufficient evidence to support the claim that the population mean of all birth rates is less than 200 pounds. All right, so again, the wording just comes from the sentence right here. There's not sufficient evidence to support the claim that the population mean of all birth rates is less than 200 pounds. We are done. I want to show you the p-value as well as the technology. For the p-value, by the way, the area to the left of test statistic, this would be this is the test statistic. So the green one is alpha. The blue one is the p-value, because p-value is larger than alpha. Fail to reject the null hypothesis. But what is numerically the value of that? You can look up the table, the Z table, area to the left of that. Or if you go with the technology and do mean Z test, one mean Z test, you plug in mu sub 0 is 200, sigma x bar n, and again, you choose one of those, you move it to the left or right. and less than results in this. And look at the numbers that we are interested in. First and foremost, this z-value is the test statistic. It's very close. Here's the p-value. The p-value is 0.151, let's say, which is larger than alpha of a 0.1. Because it's larger, we have the same decision, which means fail to reject the null hypothesis. "16 new textbooks in the college bookstore had prices with a mean of $70.41 and a standard deviation of 19.70. Use a 0.05 significance level to test the claim that the mean price of a textbook at this college is less than $75. Assume normal population, because n is small. When I say small, it's smaller than 30. They have to give us either that it's normally distributed, or we are going to assume that, therefore we can use the process. First and foremost, 16, that's n. Then the mean goes back to those 16, the mean of those 16. So this is x bar 70.41 and standard deviation of 19.7. Again, this goes back to those 16. So that's S. Alpha is 0.05, mu is 75. So this is given from reading the question. Let's go with H0 and H1. H0, mu 75 equals 75, and H1 mu is less than 75, and that happened to be the claim. Again, it's a left tail test, LTT, left tail test, and it happened to be the claim. Again, not always the case. In this case, the test statistic uses T equals X bar minus mu over S over square root of n, because population standard deviation sigma is missing. So I repeat, in this case, we use T because sigma, the population standard deviation, is missing. Let's plug in those values, X bar mu S n, and we end up with this number, which becomes negative 0.9320. Again, with the traditional method of using critical value, alpha is given to be 0.05. Degrees of freedom is n minus 1 or 15. And we can find the value of T somehow, for example, to remind everybody from the table. So you're looking up the left column, number 15, over here. The area in one tail is 0.05, so 1.753. Because this is a left tail test, the answer is negative 1.753. Now, in a matter of comparison, if you do the drawing, again, let me do it by hand and I'll show you a better drawing. So the CV, this is alpha over 0.05, and this is CV equals negative 1.753. So where does this go? Negative 0.9, somewhere here. So this is not inside the rejection region. Again, failed to reject the null hypothesis. And of course, this is a better graph. So T is negative 1.753, alpha is 0.1, and this number negative 0.932 is somewhere in the non-rejection region. Therefore, fail to reject the null hypothesis. So if we are not rejecting the null, that means we are rejecting the alternative. So the claim becomes false. Then there is not sufficient evidence to support this claim that the mean price of a textbook is less than $75. So fail to reject the null hypothesis because the value of test statistic is inside the non-rejection region. Claim becomes false. There is not sufficient evidence. And the wording just comes from the given. Let's do this with technology quickly because I want to explain again the p-value. The p-value, by the way, refers to this area. The green one is the alpha, and this blue one is the p-value, which is, I mean, from the graph, it's larger than 0.1, but let's find out what it is. So we put the information, mu is 75, xy is 70.41, and s is 19.7 because we are using t-test. N is 16, again, less than. When we do the calculation, this is the information. And notice it gives you the X bar and S and N back. So what are those values? First and foremost, we calculated the test statistic here, didn't we? Secondly, here's the p-value, 0.183. This p-value, which is the shaded region in blue, is larger than alpha of 0.05, and we get the same decision, which means fail to reject the null hypothesis. Could somebody read this?
Tests in the author's past statistics classes have scores with a standard deviation equal to 14.1. One of his current classes now has 27 test scores with a standard deviation of 9.3. Use a 0.01 significance level to test the claim that this current class has less variation than past classes. Does a lower standard deviation suggest the current class is doing better? Assume the population is normal.
Perfect. Again, let's read and write symbolically. We are assuming normal distribution. 14.1. The past statistic classes have a score of standard deviation of 14.1. That is a population. Sigma is 14.1. But one of the current classes, n equals 27, the test scores have a standard deviation of 9.3. So for those 27, standard deviation is 9.3, makes this S. Alpha is 0.01. And we are testing the claim for either the standard deviation or variance, makes no difference. So normal distribution, sigma is 14.1, n is 27, s is 9.3, alpha is 0.01. I had told you before why we want to go with the symbols, because in this case, there are two standard deviations, this one and this one. One of them is population, one of them is a sample. We should distinguish between the two. So the first step is similar to what we had, H0 and H1. H0 sigma is 14.1 and H1 sigma is less than 14.1, and that's the claim. Again, it happened to be a left-tail test, and that's the claim. Now, sometimes they may use sigma squared class, and that's fine. if you use sigma squared, this is 14.1 squared. Sigma squared less than 14.1 squared. So you could use sigma squared, but don't forget to square this one. So I'm going to write underneath and I'm going to clean it up. So if you use sigma squared, then it's not 14.1. You have to square it. And the same thing here. Sigma squared less than 14.1 squared. You put it into a calculator, you do the math. That is extremely important to be careful of. The next step is test statistic. And test statistic for this is chi-squared equals n minus 1 times s squared over sigma squared. So test statistic is calculated in this manner. We have all the information, plug in. That's why this given really comes handy. Plug in. You don't have to look for it again. You wrote it in the beginning. Plug in. (27 minus 1 times 9.3 squared over 14.1 squared), and it simplifies to 11.311. The third step is CV. Alpha is 0.01. Degrees of freedom is n minus 1 or 26. This is a left tail test. So the area to the left is 0.01. And remember, for chi-squared, we need the area to the right, which makes it 0.99. So we have this table. On the left column, we look for degrees of freedom of 26. I need the area to the right, which is 0.99. So up here in the top row, look for 0.99. And when you put them together, the answer is 12.198. So the critical value is 12.198. So basically, when you graph it, you compare the location. So here's the chi-square, the test statistic. First, you start with the critical value, has the value of 12.198. And by the way, remember that the chi-square starts from 0 and goes to infinity. We don't have a negative values. And your test statistic, 11.311, puts you way into the rejection region. So again, here's your critical value of 12.198. Here's your test statistic, which is less than that, puts you in rejection region, meaning what? Reject the null hypothesis. So if you're rejecting the null hypothesis, loosely put, you're accepting the alternative. So if the alternative is being accepted, the claim is true. So there is sufficient evidence to support the claim that the current class has less variation than past classes. So reject the null hypothesis because the value of test statistic is inside the rejection region. By the way, this, if I were to, so this whole red is alpha, and this one in blue is the p-value, which we're going to look at in a moment. So there is sufficient evidence to support the claim that the current class has less variation than past classes. However, a lower standard deviation doesn't suggest that the current class is doing better. It just means that the grade is more homogeneous, closer to the mean. So mean value might be different. That's a different story. So it just means that they are more close to each other, the students. Now, let's look at it from the point of view of the p-value you can use technology. If you go with second variables and chi-squared CDF, the upper is 11.311, the lower is 0. Degrees of freedom is n minus 126. And this value is the area to the left of 11.311. So take a look at what we wrote. Therefore, your p-value is 0.0055649898. That's your p-value. And if we do the rounding here, this one changes to 6. Clearly less than alpha of a 0.01. And therefore, because it's less than alpha, reject the null hypothesis. Reject the null hypothesis. Here's the last question. Could somebody read this one, please?
Consider a population of frogs living on an island. We believe that the frogs may be members of a species called Ranapipians. The mean length of Ranapipians is known to be 11 centimeters. The following length values, cm, were obtained for a sample of individuals from the island. You want me to read out the numbers?
No.
Do these frogs have sizes that are consistent with them being Ranapipians or not? Are these frogs Ranapipians or not? Use a 0.05 significance level.
Perfect. This is a simple example that is used in, for example, biology. And so we have collected a bunch of samples. And at this point, you have to put this into a calculator, any sort of a technology. To calculate X bar and S, we need to do that. First and foremost, there are 20 pieces. N is 20. N is 20, you count them. Alpha is 0.05. And the mean length is known to be 11 centimeters. What does it mean? Mu is 11 centimeters. So you look at the given. N is 20. Alpha is 0.05. Mu is 11. Now, you run the technology. Calculator X bar is 10.525 centimeters and S is 0.9043 centimeters. And now we are going to go with the test of hypothesis. The first step is H is 0, mu is 11, and H1 mu is not equal to 11. It doesn't say less than or greater than. If it's not equal to 11, then it's not Ranapipians. Otherwise, it is. So H0 mu is equal to 11. H1 mu is not equal to 11. So first and foremost, H1 gives you the tail of the test. Because it's not equal, it makes a two-tail test. So we are looking at those group and we are saying those are the type of frog we are looking for. So that would become our claim. But even if you put the claim here, when you do the writing, you can make it clear. So I'm going to put the claim next to H0. The next step is to calculate the test statistic. T equals X bar minus mu over S over square root of N. So we have T equals 10.525 minus mu of 11 over S, which is 0.9043 over square root of N, which is 12. And when you plug it into a calculator, this will give you negative 2.3491. Now, the next step is to calculate the CV. Critical value, alpha is 0.05. Degrees of freedom is n-1 or 19. And it's interesting to see that t is plus minus 2.093. I want you to notice it's a two-tailed test, so half of alpha goes here. That means this is 0.05 divided by 2, or 0.025. This is 0.05 divided by 2, or 0.025. And this is negative 2.093. This is positive 2.093. Where does this go? So first, you notice that this is less than negative 2.093. It's in the left rejection region. In the left rejection region. So according to the comparison of CV to the test statistic, reject the null hypothesis. Reject the null hypothesis. When you're rejecting the null hypothesis, that means you're rejecting the claim that goes with that, which means the claim is false, which means there is not sufficient evidence to support the claim that these frogs have sizes that are consistent with them being Rana pipiens. So reject the null hypothesis, the claim becomes false, so they are not, which simply put means the conclusion is these are not Rana pipiens. These are not the type of frog we were thinking, according to this calculation. Now, if you run the technology, in this case, this is a Excel file. Notice we have a couple of values here. The test statistic is a negative 2.349, what we have here, 1. The critical value is plus minus 2.093. Look at the p-value. The p-value is 0.02979, which is less than alpha of a 0.05. So think about this as 0.03, less than 0.05, and that means reject the null hypothesis, which is the same decision we've already made.